Sigma bonds are bonds in which the electron density is along the internuclear axis. These are the single bonds we have considered up to this point. Sigma bonds are produced by the orbital overlap combinations of SS, SP, PP in the head-to-head fashion, more on this later, and S, SP something, and P, SP something. Here's a little mnemonic maybe to help you that sigma are always single bonds. Multiple bonds result from the sideways overlap of two p orbitals, one from each atom, that are oriented perpendicularly to the internuclear axis. These are pi bonds, and a little mnemonic to help you remember that pi bonds are involved anytime there is a multiple bond. The word pi is right there in the word multiple. Now, it's written backwards, but it's definitely there. And multiple unhybridized. They both have the same vowel sound. Multiple bonds result from unhybridized p orbitals. Pi bonds are generally weaker than sigma bonds because pi bonds have less overlap. Let's consider the case of ethene, which has the chemical formula C2H4, and it has that Lewis structure. We can see that the electron domain geometry around the carbons is trigonal planar. And we said in an earlier lesson that if we know the electron domain geometry around a particular atom, then we can identify its hybridization state. And we said that for trigonal planar, the hybridization state is sp2. For each carbon atom, there are 3 sp2 hybridized orbitals. These form sigma bonds with carbon or hydrogen. So on the right side of the screen, I've shown the single bonds, the sigma bonds, between all of the atoms in ethene. This sigma bond that I'm highlighting here with my laser pointer results from the overlap of the 1s orbital in hydrogen with one of the sp2 hybridized orbitals in this carbon. That overlap results in that sigma bond. Same with all of the other carbon-hydrogen bonds. This carbon-carbon bond results from the overlap of an sp2 hybridized orbital from this carbon and an sp2 hybridized orbital from this carbon. If the hybridization state on those carbons is sp2, that means that there is a single p orbital from each of those carbon atoms that is unhybridized, that retains its dumbbell or figure 8 shape. And those unhybridized p orbitals overlap a bit. If you look at the right side of the screen, I'm using my laser pointer, you can see that there's a little bit of overlap region up above here and a little overlap down there. I'm going to hatch those regions, and those two regions together constitute a single pi bond. That isn't 2 pi bonds, it's a single pi bond. Overlap above the sigma bond, which is here in the middle, and overlap below. Those two overlaps, one above and one below, they constitute a single pi bond. As we said before, single bonds are sigma bonds. Here's a picture of ethane. Double bonds consist of 1 sigma and 1 pi. Here's another representation of what I was trying to show on the previous slide, where we have the sigma bond along the internuclear axis, and then where there is overlap between these unhybridized p orbitals, and they've tried to show it in this rightmost picture here, that is a pi bond. So you have a sigma bond there, and you have a pi bond there, above and below. Triple bonds consist of 1 sigma and 2 pi bonds. So for example, ethine, or acetylene as it's commonly known, and here's a representation of that. This solid black line is meant to represent the sigma bond, and then you can see that we have some unhybridized p orbitals. The purple ones result in overlap there and up there. That's one pi bond. And then the ones that are shown in blue, there's overlap there, and then we can't see it. It's behind overlap back in here somewhere. That's the second pi bond. Experiments indicate that all of C2H4's atoms lie in the same plane. This suggests that pi bonds introduce rigidity, that is, a reluctance to rotate, into molecules. This picture that has a black background on the left side of the screen represents C2H6, which has only sigma bonds, only single bonds. And you can imagine if you grab these three white atoms on the left with one hand and you were to grab these three white atoms on the right with the other hand and twist them, that they would spin freely. On the other hand, this picture on the right represents ethene, which is C2H4, and the sigma bond between the carbons is shown in the middle there. The pi bond is shown right up above and below. That's a single pi bond. And you can imagine if you grab the hydrogen atoms, which are the white ones, on the left with your left hand and on the right with your right hand, and you tried to twist those relative to each other, you can imagine that that pi bond would tend to resist your twisting of the molecule. That's what we're trying to say in that statement at the top. Pi bonding does not occur with sp3 hybridization, only sp and sp2, and that's because pi bonding requires unhybridized p orbitals, and with sp3 hybridization, all of the p orbitals have been hybridized. Pi bonding is more prevalent with small atoms, like carbon, nitrogen, and oxygen. That's because big atoms don't allow enough p orbital overlap for pi bonds to form. If we look at the picture in the upper right, these two carbon atoms, let's say they were silicon atoms, which is the element right below carbon. If they were silicon atoms, then this bond length would be longer. The p orbitals that go up in a figure 8 shape, they don't really overlap enough if this distance is too long. So pi bonding tends to occur only with small atoms. Let's review sigma bonds, pi bonds, and multiple bonds. 1. In a sigma bond, the electron density is concentrated between the bonded atoms. Anytime at least one s or one hybrid orbital is involved, the bond is always a sigma bond. Two p orbitals can form a sigma bond only if they overlap in head-to-head fashion, as in Cl2 or Br2. 2. Pi bonds result from sideways overlap of p orbitals. The electron density is located, say, above and below the internuclear axis, not on it. And 3. Single bonds are sigma bonds. Double bonds have 1 sigma and 1 pi. Triple bonds have 1 sigma and 2 pi bonds.